the rectangular approximation method. Alright, so the motivating question here. We've switched gears a little bit. First we were talking about derivatives, and then we jumped to antiderivatives. So you might be thinking, why are we approximating area now? So let's kind of take a look at an example. Let's say I have this graph here that represents a function, and let's say this function here is a velocity function, v of t. So on the y-axis here, I'm going to go ahead and let the units, so this is the velocity, so the units of my velocity here are going to be in feet per second. And then the horizontal axis, what's normally the x-axis or the t-axis this time is going to be in seconds. So now here, having the graph of the velocity function has its benefits. So if I were to ask the question, how fast is this object traveling at 4 seconds? So we'll just kind of write that down. So how fast is the object traveling at time t equals 4 seconds? Well, having the graph of the velocity function has its advantages. So I can go ahead and look at the t-axis at time t equals 4, and since this tells me the velocity, I can say that the velocity of the object at 4 seconds is 3. So the object is traveling at a rate of 3 feet per second just by looking at the graph at time t equals 4 seconds. But if instead I want to know how far has the object traveled over an interval, so between the time frame, that doesn't look like between t equals 0 and t equals 4 seconds. So we want to find a way to find the distance traveled. Well, that has to do with position given the velocity function. So what I'm going to do is I'm going to take a look at the area. So I'm going to take a look at the area enclosed by the velocity function and the x-axis between time 0 and 4 seconds. So I'll go ahead and draw that. So I'm looking at the area enclosed by this function between 0 and 4 seconds. So what I'm trying to do here is I'm trying to figure out this area. Well, notice this is a geometric shape that we have formed here. So this forms a perfect polygon. In fact, it forms a trapezoid. But if I wanted to, I can split it up into a rectangle and a triangle. So let's go ahead and do that. And find each of these two areas. So if I want to find the area of this rectangle here, I'm going to go ahead and say that it has a base of 4 and a height of 1. So I'm going to have 4 times 1. And I'm going to add the area of the triangle here. So the area of a triangle is 1/2 base. So the base here is 4 times the height. The height of my triangle here is going to be 2 units. So here I'm going to have 4 plus the 1/2 times 2 becomes 1. So 4 plus 4 equals a total of 8. So why did I just find the area of this trapezoid or break it down into the area of a rectangle and a triangle here? So what does this 8 represent? Well, here's what I want to take a look at. Let's think about just this rectangle for a second. So the units of the base of the rectangle, so if I think about the base of the rectangle, the units are in seconds. And if I think about the height of just the rectangle, well, the height is in units of feet per second. So to find the area of a rectangle, I have to use base times height, which we did right here when we did 4 times 1. But just to pull it off to the side for a second, if I do base 4 seconds times a height of 1 foot per second, if I include the units, well, I would multiply the numbers, so I would still end up with 4, but look what happens to my units. Seconds cancels. So I end up with units in a measurement of distance in feet. So that's not unique to just the rectangle, it applies to the entire geometric shape. So here I have 8 feet as the units of measurement of the area of the shape I just found. And it turns out that 8 feet is the total distance traveled by the object between 0 and 4 seconds. So the answer here is 8 feet, and we found that answer by computing area. So that's why we're interested in approximating the area. So in that last example, you might be thinking, well, that wasn't too bad. I can find the area of that geometric shape. But now the question becomes, what if the graph is a curve instead of a line? How do we find the area bound between a curve and the x-axis? So now let's say this curve here represents our velocity function. And I'm interested in finding the total area between this curve and the x-axis on the interval from 0 to 4. So similar question, but now our velocity function is not linear. Instead, the velocity function is a curve. So we're first going to start out by doing some approximating. So we're going to approximate the area underneath that curve using rectangles. And to make things easier, we're first going to use rectangles that each have equal width. So to find the area under this curve, let's start out with an approximation. Before we begin, we're going to make some assumptions in this particular lesson. So the first assumption is that the functions that we're dealing with are going to be continuous. The next assumption we're going to make is that the function is always positive. So let's remind ourselves what that means. A function is positive when it is above the x-axis. And then finally, we're assuming that we're trying to find the area under the graph. So by that we mean the region between the graph and the x-axis on the interval from A to B. So we're also going to be using some terminology. So A is going to represent the left endpoint of the interval from A to B. B is going to represent the right endpoint of the interval from A to B. We're going to use a capital N to indicate the number of subintervals of AB, or the number of rectangles. So as we mentioned, we're going to be using rectangles to approximate area. And to make our lives easier, we're going to have rectangles that have equal width. And big N is going to represent how many of those rectangles we have. And then finally, remember the notation here, delta means change. So the change in x, delta x, equals b minus a over n. So we're going to take the right endpoint, subtract the left endpoint from it, and then divide by the total number of rectangles we want. And that's going to give us the width of each subinterval, or the width of each rectangle. So we're going to have n rectangles of equal width, and that equal width is going to be represented by delta x. So right now they're all a little bit abstract, and we're going to make this really concrete in the next example. Alright, so I went ahead and left the terminology up here on the left for us to reference. What we're going to try to do is we're going to try to derive the formula, one of the 3 formulas that we're going to be using in this section, and figure out using the graph where it comes from. So we want to use a right endpoint rectangular approximation with n rectangles to estimate the area under the curve f of x between a and b. So on a graph, here's my function f of x. A and B is an interval on the x-axis, so let's go ahead and call this point A and this point B. I'm going to use rectangles, and I'm going to use right endpoints, and we'll talk about what that means in a second. I'm going to use rectangles and right endpoints to determine the height to estimate the area under the curve. So the area we actually are trying to find is the area between A and B. So I'll sort of sketch it out. So between A and B, bound by the function and the x-axis. So I will go ahead and highlight that area. I'm interested in finding the exact area under the curve, so this yellow portion here. But what you'll notice is that this yellow portion doesn't represent some nice geometric shape that I have a formula for. So it's not a circle or a square or a triangle, something that I have a nice geometric formula for. It's this weird shape that I'm going to need to approximate first. So why rectangles? Because rectangles have a nice geometric formula. The area of a rectangle is just base times height, or length times width. So we're going to use rectangles to approximate the area. And you'll see how we end up using those rectangles to give us an exact area. So first things first is I want to use n rectangles, so that's a generic n, but each of them has to have the same width. So to make things easier, we want each of the rectangles to have width delta x. And the rectangles start at the leftmost endpoint. So our rectangles are going to start over here at A, and they're each going to have width delta x. Since these little tick marks are here, let's go ahead and say that each of these tick marks is of width delta x. So in other words, this little portion here is of length delta x. So I need to start at my left endpoint A, and the width of my very first rectangle is going to have width delta x. So if this little distance here is delta x, then this tick mark can be represented generically by A plus delta x. So let's put some numbers on it to just help understand. So let's say that A is 1. And delta x, the width of this first rectangle, let's say this delta x is 2. Well, then that must mean this tick mark, if I started at 1 and this width is 2, that means this next tick mark has to be 3. So I added delta x to the starting value of A. So that's all we're saying here. We're just using this general terminology. So we start at A, the width is delta x, so that must force this new tick mark to be A plus delta x. So why did I do that? What I need to then do is define a height. So we have that the width of each rectangle is delta x. But to find the area of a rectangle, I need a base and a height. So my base is delta x. My height, well, I can choose any function value to be the height. So any function value between a and a plus delta x, any one of these points up here, I can choose to be the height. But here's where this word right endpoint comes in, or this emphasis on right. So what I need to do is over the little interval between a and a plus delta x, I need to go to the rightmost point and map that up to the function to define the height of my rectangle. So over this little interval, the rightmost point is a plus delta x. So if I take that point up to the function, then on the graph of f of x, if I substitute in a plus delta x, then this point here is f of a plus delta x. So it's heavy on notation, but again, remember, what if this was just the number 3? Then this point here would be f of 3. But we're just using the notation a plus delta x. So this is the point f of a plus delta x, and that defines my height. So let's actually construct the rectangle. So here, I'm going to go ahead and construct the first rectangle with base delta x between a and a plus delta x. And the height is going to be at the rightmost endpoint on the function. So the height is that black dot that I drew, f of a plus delta x. So this is my very first rectangle that approximates the area. So just taking a quick look at it, this first rectangle is going to give us a little bit too much area. So this little portion over here is going to be an overestimate, just this little portion, because all of this yellow part is included, which is great, but I'm adding some extra area in my approximation if this defines my height. So let's keep going. If this is a plus delta x, well, remember, each of these widths is the same. So this width here is also delta x. So if this is a plus delta x, then this little tick mark is a plus, well, now I've added 1 and 2 copies of delta x, so a plus 2 delta x. So then now, over this next little width, the rightmost endpoint, so every single time, because I'm doing a right endpoint approximation, over each little width, I'm going to go to the rightmost point and go up to the function, and that point is going to define my height. So now let's construct that rectangle. So it's going to have a base between a plus delta x and a plus 2 delta x. And that's going to be the height of my next rectangle. So here you'll notice, and it wasn't supposed to be that way, there's not supposed to be this little space here, but because my drawing on this program is not perfect, this should have gone all the way over. So each of these should be lining up perfectly. So I go to the rightmost endpoint over the first interval, and that's my first height. Then over the next interval, the rightmost endpoint, and that's my next height. So since this was a plus 2 delta x, on the function, this is f of a plus 2 delta x. And nothing about this is unique. The next coordinate point is, what do you think it's going to be? This is going to be a plus 3 delta x. So the next height right here is going to be f of a plus 3 delta x. So now I'm going to draw my next rectangle, which has the same width, but now height f of a plus 3 delta x. So notice my first rectangle was going to give me a little too much area, and then my next rectangle, well, it's missing some. I'm leaving out all this yellow portion here that I'm trying to find, and my third rectangle also has me missing some of the yellow part that I'm trying to approximate. So notice here it's an approximation, and so far we've only used 3 rectangles to do so. So ideally we're going to use n rectangles. So here we're just going to put a little dot dot dot, and we're going to move on to the very last rectangle. So the rightmost endpoint here is called B, but remember that we want to go all the way out to n rectangles. So what that means is that the very last rectangle, so there's going to be 1, 2, 3, all the way out to the nth rectangle. So I'm going to have how many copies of delta x? I'm going to have n copies of delta x. So B can also be written as a plus n delta x. So I'm going to have n copies of delta x because that's how many different generic rectangles I have. So that must mean that the height of my last rectangle is going to be f of a plus n delta x. So my very last rectangle over, again, a width of delta x is going to have a height of b, but we just said that b was f of a plus n delta x. So the reason we're doing this is because we're trying to come up with a generic formula, and right now it must look kind of crazy. So we're going to go piece by piece and write out the area formula for each one of these triangles, or rectangles. So the area here that we're trying to approximate, well, let's go rectangle by rectangle. So the very first rectangle, so the area of each rectangle is base times height, so the base is delta x. And the height of the first rectangle we said was f of a plus delta x. So that's the first rectangle. Plus the second rectangle. Well, the second rectangle still has a base delta x, but this time the height is f of a plus 2 delta x. And then finally, we're going to put plus dot 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 plus, because there are n rectangles, so that's in general, so there might be who knows how many in between, but until we get to the very last one. So the last one still has the property that the base is delta x, but this time the height is f of a plus n delta x. Now, we're trying to make this generic formula, so what we're going to do is see what's common throughout all of these. So since everything's being added together, and in each of these terms there's a delta x, I can factor out a delta x. So this area is delta x times the quantity f of a plus delta x plus f of a plus 2 delta x plus dot 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 plus f of a plus n delta x. So now I want to draw your attention to, and I'll use a different color, the fact that what's inside this parentheses, every single term in here is almost the same, except they vary by whole numbers, incrementally increasing by 1. So f of a plus 1 copy of delta x, I'll erase this 2 and make it blue because the next one is f of a plus 2 delta x, plus this dot 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 in the middle, the next term would be f of a plus 3 delta x, all the way up to f of a plus n delta x, where n is the rightmost endpoint of the very last rectangle. So the reason I'm highlighting this is because what we're going to do next is we're going to turn this sum into a nice little summation formula. So we're going to keep the delta x on the outside, but whenever I have a collection of terms being added together where they look almost exactly the same, but there's just one number that's increasing by 1 every time, I can use summation notation to make this just nicer, to make it more condensed. So the summation notation is the giant sigma, and the sigma needs an index. So the index starts at whatever number we want to begin the collection of numbers we're going to go through at. So we want to start this index at 1. So we're going to have j equals, I'm going to go ahead and do it in blue again, 1 to n. So summations run through all of the whole numbers starting at whatever you make the first index to be. So we want the first number to be 1, and then we're going to go up by whole numbers, so 2, 3, 4, all the way up to the last whole number n. And then we go ahead and input the generic term. So the generic term is f of a plus, well, now instead of putting the number, we put the indexing variable. So the indexing variable is j. So f of a plus j delta x. So this here is an approximation for the area underneath this curve between a and b. But we used right-hand endpoints. So we give this formula a special name. We're going to call it big R with an index of n, where big N is the number of rectangles that we use to approximate. So this formula tells us the right endpoint rectangular approximation with n rectangles to estimate the area under the curve between A and B. The next thing we'll look at is using left endpoints to approximate the area. So we're still going to have little rectangles of width delta x. So each of these little widths is delta x. And the only difference is that over each small interval, so from a to a plus delta x, instead of going to the rightmost point and going up to the function, we're going to go to the leftmost point and take that up to the function, and that's the height of our first rectangle. So this here is my first rectangle to approximate the area under the curve. And then over the next little width, I'm going to go to the leftmost point and go up to the function, and that's going to be the height of my second rectangle. So instead of going to the rightmost endpoint, going up to the function and drawing a horizontal line for the height, I go to the leftmost point, go up to the function, and then that defines the height of my rectangle over that little interval. So here, the very first height is going to be f of a. But I'm going to write f of a as f of a plus 0 delta x, because I'm going to try to create that generic formula again. And then over this next little interval, this is a plus 1 delta x. So this point on the function is f of a plus 1 delta x. And then f of a plus 2 delta x. And then this last little interval. So over the last interval, I don't want to go all the way to the rightmost endpoint on this little width. I want to go to the leftmost point. So last time we said b was a plus big N delta x. So that must mean that the point before it is a plus n minus 1 delta x. So that means that the height that I want to define for the last rectangle stops at a plus n minus 1 delta x evaluated in the function. So f of a plus n minus 1 delta x is the last function height. So here's my formula for ln, the left endpoint approximation. So the very first rectangle, the width is delta x, the height is a plus 0 delta x, plus the second rectangle has width delta x, but the height is a plus 1 delta x, and then dot 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 all the way to the last one. So over the last rectangle, I have f of a plus n minus 1 delta x. So I should be careful. This is a big N, and this is a big N. So again, delta x is common in all of them, so I can factor out the delta x here, and I'll have left f of a plus 0 delta x plus f of a plus 1 delta x plus all the way up to f of a plus n minus 1 delta x. And then this portion here, well, I'm adding terms together. They are almost the same except they incrementally increase by 1 every time, and this time my starting index is 0. So notice I have delta x, the sum of j equals 0 to n minus 1 of the exact same thing. F of a plus j goes wherever the whole numbers went. So f of a plus j delta x is still the function. So the only thing that changed between the left and the right-handed approximation is the indices. So j equals 0 to n minus 1 for the left, and for the right it was 1 to n. So those are the only difference. And just to share a little mnemonic or a way to remember this, students from last year had a very unique way of remembering this by saying that this is f of Ajax. So this looks like A, and then j delta sort of looks like an A. So they remembered this as f of Ajax, just to help as a little way to remember the formula. So now let's take a look at the formulas a little bit more formally. So the nth right endpoint approximation, also known as R sub n, or RRAM, so that stands for Right Rectangular Approximation Method. The way that it works is over each subinterval, construct the rectangle whose height is the value of f of x at the right endpoint on the subinterval. And here's our formula. R sub n equals delta x, the sum of j equals 1 to n of f of a plus j delta x, or f of Ajax. The nth left endpoint approximation, L sub n, or LRAM, means that over each subinterval, we construct the rectangle whose height is the value of the function at the left endpoint on the subinterval. And it's the same formula for Rn, only the indices have changed. So now the index of the summation is from j equals 0 to n minus 1, still of f of a plus j delta x. So the last one is the midpoint approximation. So we didn't go through the process of constructing the midpoint approximation, but we will look at it in the next example. So the nth midpoint approximation, or M sub n, or MRAM, means that over each subinterval we construct the rectangle whose height is the value of the function at the midpoint on the subinterval. So the formula looks a little bit more complicated. The formula is delta x, the sum from j equals 1 to n of f of a plus j minus a half times delta x. So the half, you should try to remember it because the half will come from the idea that we're going to the midpoint over each subinterval. So if the first interval is from 0 to 1, we're going to take the function value at 1/2. So we're going halfway between each subinterval, or each little width. So it's going to make a little bit more sense when we look at a more concrete example here. Alright, this example is going to be a bit long because we're going to calculate all three, the right, left, and midpoint approximations using 4 rectangles for the function f of x equals 1 over x on the interval from 2 to 4. So if you know what the function looks like, it's going to help to draw a little picture for yourself so that you have an idea of what you're doing. So 1 over x on the interval from 2 to 4. So 1 over x is the reciprocal function. So it looks like this. So we have this portion that's decreasing up at the top, and then we still have a decreasing function over to the bottom left. But we're not really concerned with what's going on over here. We're concerned with what's happening between 2 and 4. So we're interested in this area here. So we want to find this area between 2 and 4. But we can't find it exactly. The only tools we have so far is finding an approximation using rectangles. So let me blow this up a little bit. Let's erase this and just focus on that first quadrant. And we'll go ahead and draw the curve, and we're interested in the area between 2 and 4. Alright, so here's my function, f of x equals 1 over x. And the very first thing that I'm going to do is write out the formula for R4. So R4 is going to be delta x times the sum of j equals 1 to n, where n is the number of rectangles, so the number of rectangles I want is 4. So j equals 1 to 4 of f of a. So remember, a is 2 and b is 4. So f of 2 plus j delta x. So what I can still substitute in here is a value for delta x, provided that I find delta x. So delta x, remember, has the formula b minus a, so 4 minus 2, over n, where n is the number of rectangles. So that's going to be 4. So 4 minus 2 is 2 over 4. 2 over 4 is 1/2. So let's replace delta x with 1/2. So we have 1/2 the sum of j equals 1 to 4 of f of 2 plus j times 1/2, or 1/2 j. It's probably better if we write it like that, 1/2 j. Alright, so let's draw what we're really doing here with this right-handed approximation. So what I need is 4 rectangles with a width of 1/2. So 4 equal rectangles, so let's cut this width between 2 and 4 in half. That's going to be right here at 3, and then we want to split each of those in half again. So this is going to be right here at fractions. We'll use 5 over 2, and then here we'll go ahead and use 7 over 2. So these are going to be each of my little subintervals, and these are each going to define a base. So what we want to be interested in doing as well is constructing the right, left, and midpoint approximation on a graph. So that's what we're going to go ahead and do here. So between 2 and 5 over 2, or between 2 and 2.5, if I'm interested in drawing R4, then I'm going to go to the rightmost point over the first interval, go up to the function, and that's going to be the first height. So that's my first rectangle. Now between 5 over 2 and 3, I'm going to go to the rightmost point, go up to the function, and that's going to be my next height. Then between 3 and 7 over 2, or 3 and 3.5, I go to the rightmost point, 3.5, I go up to the function, and that's my next height. And then finally between 3.5 and 4, 4 is further to the right, so I go up to the function, and that's going to be my next height. So just a little rough sketch of the rectangles we're going to use to approximate the area. And in each of these cases, we use the rightmost endpoint. So that is one portion of a problem that you will be expected to do, is to construct or draw on the graph the rightmost endpoint approximation, or the right endpoint approximation. So that's already one portion of the problem. So now we have an idea that it looks like we're going to have an under approximation. Every single one of these rectangles is under the curve, and we're missing a bunch of area over each tiny subinterval. So now let's solve for the actual area. So we have 1/2, and now summations work by substituting in the first number of the index. So we substitute in 1 for j. So we're first supposed to find f of, if we substitute in 1, we have 2 plus 1/2 times 1, or 2 plus 1/2. So f of 2 plus 1/2 is 5 over 2 again. So a half plus f of 5 over 2 plus, so remember summations, we go to the next integer. So the next integer is 2. So 2 times a half, that's 1. 1 plus 2 is 3. So f of 3 plus, if we substitute in 3, that's 3 halves plus 2. So that's going to give us 7 halves. So f of 7 halves plus, the last point I'm going to plug in is 4. 4 times a half is 2. 2 plus 2 is 4. So we have f of 4. Now, since we drew the graph, this would have been an easy thing to do by just looking at the graph, because over the first interval, the rightmost endpoint is 5 over 2. So that means the height is f of 5 over 2, which was our first output using summation notation. Then the next one was f of 3, followed by f of 7 over 2. We're getting kind of small, but this one was f of 4. So drawing the graph can be really beneficial rather than having to plug in each of the numbers of the index of the summation notation into the function. But either way, not too bad. So now we have 1/2 times f of 5 over 2. Well, I have a function, f of x is 1 over x. So if I substitute 5 over 2 in for x, I'm going to get 1 over 5 over 2 plus, now I substitute in 3, plus 1 over 3 plus 1 over 7 over 2 plus 1 over 4. So the function's 1 over x, so all of these values I'm plugging into the bottom. So 1 over 5 over 2, 1 over 3, 1 over 7 over 2, 1 over 4. So if I add all this up, using my calculator, I obtain either a decimal answer of 0.6345 or as a fraction 533 over 840. So that's going to be the approximation of the area under the curve between 2 and 4 using a right-hand approximation. So now we can go through the process of doing a left-handed approximation. Alright, so we've moved on to a left approximation. Let's real quickly redraw the graph. So here's my curve. I want to approximate the area between 2 and 4. A and B stay the same, delta x stays the same. So that means the width of each of my rectangles is still going to be 1/2. So we're going to have 5 over 2, 3, and 7 over 2 as the missing values here. So now, over the first little width, I want to go to the leftmost point. So the leftmost point here is 2. So the function value there is f of 2. So that's going to define the first height. So over the first little width, that's my height. So that's going to be the height of my first rectangle. My second rectangle, the leftmost point, is at f of 5 over 2. So that's going to be the height. And then between 3 and 7 over 2, 3 is to the left, so that will be my next height. And then finally, between 7 over 2 and 4, 3 is the leftmost height, so that will be my final height. And if you can see here, this left-hand approximation is going to be an over-approximation because I'm going to include too much area on each of these little rectangles. So my generic formula here for L4 is going to be delta x, so 1/2, the sum of j equals 0 to n minus 1. So n is 4, so that means I want to go from 0 to 3 of f of a is 2, plus j delta x, so delta x was 1/2, so 1/2 j. So now my formula is going to become 1/2, and remember how summations work, we start with the index 0, we substitute 0 in for j, so that must mean that this whole part goes away, so I get f of 2 plus, now I can substitute in 1. So if I plug in 1, I'll get 2 plus 1/2, which is 5 over 2, so f of 5 over 2. And we can sort of see what's going on here, just like last time. We can look at the image instead. So over the first interval, f of 2 was the height. Over the next interval, f of 5 over 2 was the height. Over the next interval, f of 3 was the height. And the last interval, we don't use the right endpoint, we use the left endpoint. So f of 7 over 2. So if we're doing a left approximation, we're starting with the leftmost point and going all the way to the second to the last one. So I don't want to use the last one. So f of 2 plus f of 5 over 2 plus f of 3 plus f of 7 over 2. So I could have got that by still plugging in all the indices of the summation. So now I'm going to have 1 over 2, and now I substitute these values into the function. So I'll get 1/2 plus 1 over 5 over 2 plus 1 over 3 plus 1 over 7 over 2. And using my calculator, I get as a decimal 0.7595 or as a fraction 319 over 420. So both of these are the exact answer, so either of these will do. Whenever possible, use an exact answer, but both are exact, so either is fine. So these are approximations, which you can tell are going to be an over approximation to the actual area under the curve that we're trying to find. So the last thing we're going to do is solve for M4, the midpoint approximation. Alright, this next example is going to be a little bit harder to see, so we're going to use decimals to show where this midpoint is coming in. So we're going to calculate M4 still for the same function over the same interval. So the formula for M4, let's write that down, is delta x, so it's 1/2. The sum of j equals 1 to n, so the number of rectangles is still 4, of f of a, so a is 2, and here's where it gets different. So f of a plus j minus 1/2 delta x. So delta x is 1/2. So here it's a little bit tricky notation, but I want to focus on what's going on the graph. So here's my function 1 over x. So I still want 4 rectangles of equal width. So here are each of my 4 rectangles widths. So each of these is 1/2. But notice that I used decimals instead of fractions this time, because now over each little width, instead of going to either the left endpoint and going up to the function or the right endpoint and going up to the function, I'm going to choose the midpoint over the interval. So here, now that it's decimals, it's easier to see that between 2 and 2.5, the halfway point is 2.25. So we're going to use that midpoint and go up to the function, and that's going to define the height of my rectangle. So the first rectangle is going to have the height f of 2.25. And now over the next rectangle, or the next width between 2.5 and 3, the halfway point is 2.75. So now the height of my next rectangle is going to be f of 2.75. And so on. So now this one is going to be 3.25 and this one's going to be 3.75. So each of those are going to define the height of my rectangles. So f of 3.25, and then this one was f of 3.75. So let's go ahead and use the formula just so that we can see the first value come out as expected. So if we substitute 1 into j, so we're going to have 1 minus 1/2. So 1 minus 1/2 is 1/2. 1/2 times 1/2 is 1/4. 2 plus 1/4 is 2.25. So this first function value to come out is f of 2.25 as expected. But it was a lot easier to look at the graph and break up the interval like that instead of using the summation notation. So f of 2.25 is the very first height. And so we can see what the other heights are going to be because we drew it on the graph. So this will be f of 2.75 plus f of 3.25 plus f of 3.75. And so now we have 1/2 times f of 2.25, so this is going to be 1 over 2.25 plus 1 over 2.75 plus 1 over 3.25 plus 1 over 3.75. And using our calculator, we get that the midpoint approximation is, the decimal answer is going to be 0.6912, and the fraction answer is really messy. It's 4,448 over 6,435. So now we've computed R4, L4, and M4 for the function 1 over x on the interval from 2 to 4. In this next example, we're going to calculate R6, L6, and M3 on the interval from 1 to 13, given the following table of function values for f of x. So we're not explicitly given f of x, we're just given points on the graph of f of x. So the point 1, 2, the point 3, 4, the point 5, 8. So we're going to take some time to go through R6 using the formula that we have and then doing a graphical representation, but then we're going to calculate L6 and M3 using a little bit of a shortcut notation, or just shortcuts, meaning that we understand the concept behind using these rectangular sum approximations. So let's focus on R6 first. So to find R6, we're going to need delta x. So let's calculate delta x off to the side. Delta x is going to be b minus a. So b minus a is going to be 13 minus 1 over n, the number of rectangles. So the number of rectangles here is 6. So we're going to have 12 divided by 6, or a delta x of 2. Now, I want to draw your attention to the table. Notice that the increments between x values is of equal width every time, or equal distance, and each of these distances is 2. So we could solve for delta x using the formula b minus a over n, or we could recognize that there's exactly 6 intervals here, each of equal width 2. So R6 using our formula is delta x, so 2, the sum of j equals 1 to n being 6, of f of a. So a, the first value, a is 1, plus j delta x. So delta x was 2, so plus 2j. So now if we want to expand all this out, it's going to be 2 times this sum. Well, if we plug 1 in first, 2 times 1 is 2, plus 1 is 3, so we're going to have f of 3. Plus, now the next one we're going to have, if we substitute in 2, the next whole number, 2 times 2 is 4, 4 plus 1 is 5, so it's going to be f of 5. So just to again take a quick second before we move on, notice that over the first interval from 1 to 3, we used the rightmost endpoint, 3. The function value there is f of 3. So we used f of 3. Now over the next interval would be from 3 to 5. So between 3 and 5, 5 is on the right, so the function value at 5 is f of 5. So using that pattern, what do you think we'll use next? Between 5 and 7, the rightmost endpoint is 7, so the function height is going to be f of 7, plus f of 9. So between 7 and 9, we're going to have the rightmost point, which is 9, so f of 9, plus between 9 and 11, f of 11. And then finally, between 11 and 13, we're going to use f of 13. So here we have 2 times the quantity. So now we have to substitute in the value. So f of 3, so here's 3, so f of 3 is 4. So we're going to add 4 plus f of 5 is 8. So notice we're just moving right along this bottom column. So what are we adding? We're adding 4, 8, 4, 10, 8, and 4. So 4 plus 8 plus 4 plus 10 plus 8 plus 4. So now we have 2 times 4 plus 8 is 12, plus 4 is 16, 26, and 12 is 38. So 2 times 38, or 76. So we found R6 to be 76. Now, we did use the summation notation to begin with, but if we just think about it as over the first interval of width 2, we're looking at the rightmost endpoint, so we're looking at f of 3, where f of 3 is 4. We've now found our very first value that we're adding together. So if I'm doing a right-handed approximation, I skipped the first point because that's the leftmost endpoint, and I started with the next one, and I went all the way to the very end because that includes the rightmost endpoint. So on a graph, let's just try to do a couple of the points just to see what's going on a graph. We have little snapshots, so we know that on the function at 1 we have a y value of 2. And then we know when we substitute in 3, we have out a y value of 4. So 2, 3. We then have a y value up here at 4. And then over at 5, we're going to have a y value of 8. So that jumped way up there. So now, if we think about it, we have these points on the graph. We don't know exactly what it looks like. It could do some crazy thing like this. We're not sure. So we have some points on the graph. So over the first interval from 1 to 3, because my delta x value is 2, so delta x equals 2. So if I'm using a right-handed approximation, then over the interval from 1 to 3, the height that I use is f of 3. Well, that height we said was 4. So over the first interval, this rectangle is going to have height, the function value at 3, which was 4. So we can do the same notion. We're doing the same thing. We're just given the information in a different way. So tabular data of this form can actually be really easy to work with if we sort of understand what's happening when we're being asked to find R6, L6, and M3. So each of these represents one rectangle. So this is the base of one rectangle, and this is the base of another rectangle, and so on and so forth. So there's going to be 6 rectangles here. And each of the delta x's is going to be 2, so the difference in each of these cases is 2. So now over the first width, the rightmost endpoint is 3, the height there, 4. So that defines my height. So there's kind of that nice little shortcut that you can implement. So let's try to implement it finding L6. Alright, so to calculate L6, we're going to go ahead and try to use a little bit of a shortcut here. So we want to use 6 rectangles of equal width. So the first rectangle is going to be between 1 and 3 with a width of 2, then between 3 and 5 with a width of 2, between 5 and 7, between 7 and 9, between 9 and 11, and then between 11 and 13. So here's my 6 rectangles, 1, 2, 3, 4, 5, 6, each have equal width, so my delta x value is 2. So L6 is going to start out with my delta x of 2. And then what I need is the height of each of my rectangles. So over the first rectangle, between 1 and 3, I'm going to use the leftmost value's function value as the height. So what I want the height to be is f of 1. So I'm going to start with the first height of 2. Now over the second interval between 3 and 5, I'm going to use the function value at 3, which is 4, to define the height over this next little rectangle. So the next height is going to be plus 4. So now the next one. So over the next rectangle, the width is 2 between 5 and 7. Between 5 and 7, the leftmost point is 5. So the function value at 5 is 8. So that defines my next height. So continuing on, I'm going to add the next function value's height at 4, the next one at 10, the next one at 8, but I don't include the last number. I don't include 4 because the last rectangle between 11 and 13, the leftmost endpoint is going to happen at the function value at 11, which is 8. And that's the only endpoint I use, the left endpoint, because I'm calculating L6. So I need to make sure that I'm adding up 6 different heights because I'm going to have the width times the sum of each of the heights, and I need 6 heights because I need 6 rectangles. So I want to make sure and not include the last one. So here I can go ahead and add this together. I'm going to have 2 times, here we're going to have 6, and 8 is 14, and 4 is 18, and 10 is 28, and 6 is 36. So 2 times 36 is going to give me 72. So a left-handed approximation to this function f of x is 72, which is pretty close to the other value that we found of 76. So we know that our answers aren't too far off, which is a good thing. We wouldn't want 2 completely different answers or we might question our results. Alright, so the last one we're going to do is compute M3. So what we need to do is we need to come up with 3 rectangles of equal width. So I'm going to erase what I drew up here because that was finding 6 rectangles and each of those equal widths were 2. So now between 1 and 13, so if we want to, we can find delta x by using the formula. So delta x equals b minus a, so 13 minus 1 over n. N in this case is 3. So what we have is 12 over 3, or we have 4. But if we don't want to go through the process of finding delta x using the formula, what I know is that I need to have 3 rectangles of equal width. So I also need midpoints, so I need the point halfway between each of those rectangles. So between 1 and 5, that's going to be 1 width of delta x, and I know that that's a good choice because I have the midpoint. So halfway between 1 and 5 is 3, and I have that function value's height. So that one is fine. And now I can go between 5 and 9, which is 4. The first one's delta x was 4 as well, and I have the midpoint between 5 and 9 is 7. And then finally between 9 and 13, my delta x is still 4, so each of these are uniform, the same delta x, but I have the function value halfway between the midpoint between 9 and 13. That function value is 8. So if I compute M3, the formula is delta x. Well, delta x in this case is 4. And over the first rectangle of width 4, I need the height defined at the midpoint. So the height defined at the midpoint 3 is 4. So I'm going to add 4 plus, now I'm looking at the midpoint again, the function value is 4 one more time. And then finally I'm looking at over the interval from 9 to 13, the midpoint is 11, the function value at 11 is 8. And now we're adding 4 times 4 plus 4 plus 8 is going to give me 16, and 16 times 4 is going to give me 64. So using midpoint approximations, I get an area of 64. So now we're going to look at whether or not we can determine if our approximation is an overestimate or an underestimate. So given a strictly increasing function f of x, if we use left endpoints, we will have an underestimate for the area under the curve. So for these things, I really don't recommend memorizing so much as just understanding how to draw the left and right endpoint approximations and knowing what an increasing function looks like. So strictly increasing meaning that the y values are getting bigger and bigger, so they're not just staying the same. The y values are getting bigger, so this square root function will work for an increasing function. So if we use left endpoints or a left endpoint rectangular approximation, let's say between 1 and 2, we're going to go to the leftmost endpoint and then draw the height of the rectangle, and you'll notice just by drawing one rectangle, we're below the actual area. We're an under approximation. So let's go ahead and erase that. And then if we use right endpoints, we'll get an overestimate. So between 1 and 2, if I go to the rightmost point and that defines my height, now all of a sudden I have all this extra area here. So now I have an overestimate. So in a strictly increasing function, if we use left endpoints to determine the height of the rectangular approximation, we'll have an underestimate. And then using right endpoints will give an overestimate. Now if we're given a strictly decreasing function f of x, using left endpoints to determine the height of each rectangle will give an overestimate. So again, between 1 and 2, if I use a left-handed endpoint approximation, now my height is going to give me a rectangle that gives me a lot of extra area. So using left endpoints is going to give me an overestimate in a decreasing function. And then using right endpoints between 1 and 2, 2 would define my height. And now all of a sudden my rectangles are below the x-axis. So using right endpoints is going to give me an underestimate. Alright, so far we have this way of finding an approximation to the area under a curve using rectangles. How do we find the exact area? So I said at the very beginning, using these rectangles, we were going to have a way to find the exact area under a curve and not just an approximation. So if we just take a look at this one function here, and we look at what happens when we use rectangles to approximate the area, but we increase the number of rectangles every time. So in this first example, well, here I have definitely an over approximation of area. I have all this extra area here, so it's not a very good approximation. But if I look at what happens when I go from 2 rectangles to 4 rectangles, well, now the amount of extra area has gone down. So it's a better approximation than it was when using 2 rectangles. And then when I use 6 rectangles, well, now look at this first rectangle. I only have this little bit of extra area here. So it's not too bad of an approximation. And in fact, it's getting better and better, you'll notice, as we increase the number of rectangles we use. So what's happening here is we're increasing the number n of rectangles. So what we should think about is that the number of rectangles, if we can get it to get bigger and bigger and bigger, or approach infinity, then we would have a really, really good approximation. In fact, so much so that it would be the exact area. And if you're thinking of the word limit, then I would definitely say that we've gone a long way, because limits is what ties everything together. So what we're going to do is we're going to take a limit of these sums of rectangles. So the last theorem of this whole section, that was really long, I know, says that if f of x is a continuous function on a to b, then the endpoint and midpoint approximations approach the same limit L as n approaches infinity. So if we increase the number of rectangles, and that number of rectangles goes off to infinity, then the limit as n approaches infinity of the right endpoint approximation is the same thing as the limit as n approaches infinity of the left endpoint approximation, and that's the same as the limit as n approaches infinity of the midpoint approximation. They all go towards the same limit, and that limit is L. So L is exactly the area under the curve from A to B. So that's how we use rectangles to find the exact area under the curve, is we let the number of rectangles go to infinity, so that each of those delta x's, each of those widths, gets really, really small and is a better and better approximation, so much so that it's the exact area under the curve, and in this case we're calling that L. So if this limit exists, then we would say that we can find the exact area under the curve from A to B.